My name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and we're hosting today's webinar series on graphene and energy storage devices, including batteries and supercapacitors and all those different chemistries that are working on in this sector. Next speaker, so we have Dr. Michael Watson from First Graphene. He's going to be talking about graphene metal oxides for supercapacitors.
Thanks very much, Terrence, for the introduction, and thanks for everyone for tuning in. There's lots of people in the audience, so thanks very much for attending. I am Michael Watson, Senior Materials Research Scientist for First Graphene, and I want to talk to you about our new materials, which are graphene metal oxides, which are used in supercapacitors, or for use in supercapacitors. And so I'm going to split up the talk into a few different parts. I'm going to give you an introduction to First Graphene and what we do, what we make. I'm going to give you an introduction into supercapacitors, what they are, why you should care about them. And I'm going to tell you about our new materials, the metal oxide materials we've produced, what metal oxides are, what metal oxides we use are, and why we're using graphene in combination with metal oxides. And then I'll finish up with just a bit of an outlook for our materials and what we plan to do in 2020. So I'll start off with First Graphene and who we are. So there's a lot of information on this slide. I'll just pick out the few key pieces of information. So we are a material technology company, but primarily we manufacture and supply graphene nanoplatelets. We have our production facility in Henderson, Western Australia, and we have our R&D facility inside the University of Manchester in the Graphene Engineering and Innovation Centre in Manchester in the United Kingdom. We have our substances registered in the United Kingdom, Europe, Australia, so we can sell into those regions. And what do we sell? We sell high aspect ratio platelets, graphene platelets, pristine platelets, which we call pure graph, and we have the capacity for about 100 tons a year of that product out of our manufacturing facility in Henderson, and we can supply them at different platelet sizes. That's how we supply them. So I just want to talk about how we actually produce these platelets and why metal oxides and graphene fits so well in our company, and why it fits so well, why this technology fits so well in with us. If I just start on the left-hand side, so we start with graphite. So we have a top-down exfoliation process. So we turn graphite into graphene. We start with very high purity graphite, very low metal ions, very low metal content, very low silicate content. We have our electrochemical exfoliation step, which lifts off those graphene layers from the graphite. We have a very high yield in that process and low waste, and it's really this electrochemical process that's key for the rest of the presentation. We then finish that graphene. We go to our industrial finishing steps, quality assurance. We have standard tests that we go through, and then we end up with our graphene materials, and we have a range of them. And primarily it's our pure graphene platelets, and they are supplied in a powder or a dispersion, or we do cement admixtures and concrete cement grinding aids, inks and coatings. We do polymer master batches, but the newest material that we're coming out with is the graphene metal oxide hybrid particles. And so if I just go on to the next one, so this is why our process is so intrinsic. So this is a little bit about the timeline about these graphene metal oxide hybrid materials. So obviously graphene was first isolated in Manchester University, where we are now, in 2004. And then during the 2010s, electrochemical exfoliation of graphite to graphene was developed, and First Graphene have scaled that process. Now we've got that process at scale, and we can supply our graphene platelets at scale. And then on another sort of trajectory was early work in the 70s and 80s on ruthenium oxides for supercapacitor materials by electrodeposition. And so that's where these two streams kind of come together. And Ejego and Drive, also at Manchester University in 2018, came out with this paper, which was where they take the graphite exfoliation, they take the metal deposition, and they combine the two processes, and you end up with a hybrid graphene metal oxide particle, which you can use for supercapacitor materials. And so they demonstrated a very high capacitance per gram, about 500 farad per gram. And so what does that mean? How can we use this in the real world? So if I go on to just a little bit about what is a supercapacitor and why it's important. So they are energy storage devices. Supercapacitors are energy storage devices. They're a broad class of devices. I'm just going to refer to everything as supercapacitors in this presentation. They lie somewhere between capacitors and batteries. So the capacitor, where there's no chemical reaction, you've got the separation of charge, you've got the polarized dielectric, and you've got batteries on one side where you've got the chemical reaction, ions are exchanged with the electrolyte. And then you've got supercapacitors in the middle, which can be a combination of these two technologies. So you've got the non-chemical reaction and the chemical reaction, which can happen either at one of the electrodes, both the electrodes. So yeah, there's different sort of setups for supercapacitors. It's really defined as a device which stores more energy than a capacitor, but delivers it at a higher rate than a battery. And so I'll just show you quickly where these materials are, or where these devices are mapped. So this is the Ragone plot. We've got energy density on the x-axis, the power density on the y-axis. You can see that batteries are to the bottom right. They're energy dense. They're not power dense. If you can think of it in terms of an electric vehicle, this is your cruising range from batteries. So you've got a very long cruising range on a battery, but relatively low power. And a capacitor, you've got high power, not very much energy stored in there. So short cruising range, very high power delivery, high charge rates. And then in the middle, you've got these electrochemical supercapacitors. And at the moment, they exist currently. And what we want to do is use our graphene metal oxides to expand the range of those electrochemical supercapacitors up to the top right of this Ragone, so we can deliver devices. Obviously, we supply the material, but the aim is to deliver devices which are high power and high energy devices. So what's available on the market currently for electrochemical supercapacitors, and where is the advantage in using metal oxides and graphene? So this is current technology for supercapacitors. So we have two kinds. We have the electrical double layer capacitance, so there's no chemical reaction inside these cells. You've got activated carbon on both electrodes. You have an electrolyte. The charge builds up on both sides of the capacitor, and the energy is limited by the surface area of the activated carbon and the potential of the breakdown potential of your electrolyte. You can increase the power density of these cells by lowering the resistance of the cell, and these are commonly available, really common supercapacitors available. If you look them up, if you look up supercapacitor, it will probably be one of these kinds. There'll be activated carbon in there, in the electrodes there'll be nanotubes. There might be graphene in there as well. The other kind that's already available is the lithium-ion hybrid. These are a slightly lower power device, so they're limited by the lithium-ion battery technology. They supply higher energy, so they're more energy dense than the double layer capacitors. They have the lithium-ion technology on one side and usually just an activated carbon on the other. And that's available, energy dense, not as power dense. And so if we map them out just for these sorts of technologies, we can. So now if we look at what our graphene metal oxide supercapacitors can do, so if we are supplying these graphene metal oxides as an active material, we can. So there's several advantages. So instead of just being an electrical double layer capacitor, so if you take the capacitor on the left, you can see the substrate on the bottom there. That's just the activated carbon. you've got your electrical double layer capacitance. The metal oxide graphene has a high surface area, so it will also act as an electrical double layer. It also has the properties of being pseudocapacitive. So that means that you get very fast redox reactions, exchanging ions quickly with the electrolyte. And that happens on the surface. So these metal ions in the metal oxide, they change oxidation state very quickly, and you can store more charge on the surface. It doesn't take as long as intercalation of lithium or any ions from the electrolyte in a battery or in the lithium ion hybrid supercapacitors. It happens much more quickly than that. And that's why it's called pseudocapacitive, is that those ions are, it almost acts like almost acts like a capacitor rather than a battery, even though there are chemical reactions going on. It doesn't rely on that intercalation. So there's two sorts of setup we could do. We could have metal oxide on both sides, different metal oxides, or we could have the asymmetric style where we would have activated carbon on one and the graphene metal oxide on the other. And so if I put these all on a map, so these are where these materials would sit. So the existing technology would sit around here. The lithium ion hybrid capacitors would sit next to batteries. We've got the activated carbon double layer capacitors at the top left there, the electrochemical supercapacitors chart. You've got your traditional capacitors at the top left. And then into this new area, we're looking to develop these and build these new hybrid graphene metal oxide devices and push into this high energy, high power area, which hasn't been explored yet. And so so metal oxides are obviously very useful and they exhibit this pseudocapacitive behavior. So why do we need graphene in there? And also, why aren't metal oxides used currently in devices that you can buy on the market at the moment? So what's the reason for that? And the reason is metal oxides have a couple of drawbacks, which are addressed and mitigated partly by the graphene. And that's why these hybrid materials are so interesting, is that metal oxides aren't very electrically conductive. And so by depositing these metal oxides onto a graphene substrate, we're able to increase the overall conductivity of the system. And so, yeah, having that intimate contact between the metal oxide and the graphene increases the electrical conductivity. So it also synergizes quite well with the graphene, because the graphene, the metal oxides stop the graphene reagglomerating. So once you've dispersed this and dried it out, it stops the graphene restacking by having those deposited metal oxides on the surface of the graphene. We also can increase the cycle life by having those oxides directly deposited on the surface. Metal oxides in a supercapacitor would traditionally sort of dissolve into the electrolyte, and they would also crack as they change oxidation state. As you oxidize and reduce the metal ions, they form different structures, and therefore you can get breakdown of the metal oxides. By having them in contact with the graphene, we can reduce that. We can reduce the effect of the solvation and the breakdown of these metal oxides by having that contact there. We're also increasing the surface area, or the accessible surface area. So these metal oxide nanoparticles are, they are quite high surface area materials, but then you're also combining that with graphene. And then one of the benefits of this is the whole system would be supplied as a powder. So you would get these graphene platelets coated with metal oxides. It would be supplied as a powder. It would be able to fit into currently available processes, and you'd have these new materials ready to be used as electrode materials. Another advantage is that we know that this process is scalable. We've already scaled our pure graph platelet process, and so we know that we can scale this only slightly modified version of electrochemical exfoliation, and we know we can get metal oxide coated graphene platelets. So if I just, so this is actually a picture of them. So this is an SEM image of these nanocrystal clusters on the surface of a graphene platelet. So this is what we've been working on, just to sort of realize it, just to sort of show you, demonstrate it there, that this is the material that we're working on. And this is just a bit of a timeline of what we've been doing. So the paper was published in 2018. We initially had nothing to do with the paper, but it was just a really interesting technology for us, and we knew it would fit well with us. We licensed that in 2019, and then we modified it slightly to fit with our process, and we've done that. We've now got it in a single vessel instead of with a membrane. We've now started to, well, in mid 2020 we started to do standard coin cell tests with standard slurries instead of just testing the material directly, which, you know, a lot of papers do. They just test the material directly. They don't formulate it into a slurry. But that's what we want to demonstrate. We want to show real results in standard coin cells with a standard slurry. And then we've also started to move on in mid 2021 to electrolyte optimization. So we know that this system needs to be optimized, and the electrolyte needs to be optimized in tandem with the material. So that's what we've started to do. And then we announced a new peak energy density at the end of 2021. So if I'll just move on to the next slide. So this is the announcement that we came out with. And so it was really just to prove and show that we can still demonstrate the pseudocapacitive behavior. These materials, they were in a slurry, they were in a standard coin cell, and we're still be able to demonstrate improvements. That, you know, we can show this increased specific capacitance in a standard formulation, and we're able to show that high capacitance of these materials, and we can do it, you know, repeatably, and we can do it at scale. And these were of the platelets which were grown in our process. The nanoparticles were grown on the surface of the graphene, and then used in the slurry formulation, and we got high gravimetric capacitance for these materials. So what do we do now that we have these materials? Well, our aim for 2022 is to develop and test a meaningful prototype device. So we have received an award from Innovate Edge, and we're really excited to use that with the University of Warwick at WMG, and we'll be optimizing the electrolyte, we'll be optimizing the separator, and we'll be demonstrating a pouch cell using these materials. And we'll be continuing to work with device makers to produce a high-performing commercial cell. So thanks very much to Innovate UK Edge and our academic partners that we've been working with, who have been really influential in getting this material realized and demonstrating its performance benefits. So I just wanted to say thanks very much to them. And if you have any questions at all, whether it's with regards to this material or also our pure graph platelets or any other sort of graphene materials, we have the expertise to talk about it, to look at your application with you. What I haven't mentioned in this presentation is that the pure graph platelets can be used as battery additives as well. So it's not just the supercapacitor materials that we're working on. We're also looking at pure graph platelets for thermal and electrical, conductivity in other sorts of cells as well. So yeah, please talk to us about any sort of application you've got regarding graphene. I'll go back to Terence.
Thank you, Michael. Appreciate that very much. And we'll distribute the slides for all of the presenters following this session. So Michael, if you want to take down your slide share or just stop sharing, then we'll do this as a chat. And then I also invite Dexter, if you have any questions, feel free to jump in. I just have a quick question just on process. So Michael, you mentioned you have an electrochemical process for making the graphene platelets that you make. Is it one pass that you do to make these metal oxide combination materials, or is it a sequential process? And
That's
then,
exactly it. Yeah. Sorry, I'll answer that one first, if that's all right.
yeah,
Is that
sure.
okay?
Please go ahead.
So yeah, it is. It's a one-step process. So it's great, that technology that the University of Manchester has been working on, Drive and Ajagu. They are, that is a one-step process. So instead of just exfoliating platelets and then having to go through another cycle or another reactor or mixing metal oxides in or something like that, we're doing this all in one step. So we are depositing and exfoliating at the same time in a controlled way. And yep, then the product comes out. It is one step. Yeah.
Understood. And is this done now on a pilot line that you have in Manchester, or is it part of your normal production line? And so the question would be, are you stopping? Do you have to change your process for what you're producing?
That's it. Yeah. So we would have to. So this work is being done in the R&D labs in Manchester at the moment, and will be scaled to the pilot scale facility in Henderson. Yep. There's we do have a pilot line in Henderson as well as kind of smaller scale production line that we can test this on. So yeah, that's where it's being done. It's being done between those two things. It's being done here. The research is being done here, and then when we get something that's promising, it's being done on the pilot scale production facility. So that's the sort of pilot line that we're running in. Yeah.
And so the audience knows First Graphene is a tier 1 partner at the Graphene Engineering Innovation Center at the University of Manchester. So when you say here tonight, Michael, you're in Manchester, UK, and then you have Henderson, Australia for the production for First Graphene. So if you scale this technology, then it would be like a parallel line. It would be a separate dedicated line in Henderson.
Exactly. Yeah. So we wouldn't be. It would be a totally different material for totally different applications. It would be a different product. It would be different to anything that I think we've come out with before, which has been our pure graph platelets, but dispersed or prepared in a specific way for these different applications. This would be a separate material, which is still based on pure graph, but it has been chemically decorated with these metal oxide materials. So yeah, it would be a separate line. But yeah, we've got that in hand. Don't worry about that.
Cheers. Thanks. Dexter, did you want to jump in with a question?
Yeah, I guess it's one of your Ragon plots where with the graphene metal oxide materials, you were able to sort of push further into the energy density realm of the sort of typical batteries. How far do you think you'll be able to push into that area and still have the high power density of a capacitor? I think, where do you see the limits?
Yeah, what we're targeting is 10 and 10, so 10 watts per kilo and 10 kilowatts per kilo as well. So that's our target. That's where we want to get to. We see these materials being used in conjunction with existing battery technology. So we think that you would end up with a hybrid device of different battery technology, something for longevity, something for energy storage, but you would use these supercapacitors. They would be more attractive as an option if they could push into that space, if they could push into that high energy, high power density. If we can get we can get something like that, and use that in conjunction with other technologies as well. We just want to make that supercapacitor more attractive, or the most attractive option, and have a hybrid device where we use traditional battery technology and supercapacitors for power management and things like that. That's where we see it, definitely.
So you see them working in tandem with typical lithium-ion chemical batteries.
Yeah, that's exactly where we see it. Exactly.
Mm-hmm. With some of the other battery technologies, there's issues with expansion of the materials. Do you have any information on how this material performs from that perspective, or heat management issues, anything along those lines?
Yep. Information, we could, in terms of charts or something, I'm sure we could get it. But if it was just talking about expansion or degradation, metal oxides suffer from this already, and that's why they're not commercialized. That's why they're not available in supercapacitors at the moment. So the graphene's really solving the problem there, rather than introducing something which might expand or something. We're really addressing the issue of metal oxides and why they aren't taken up. So they do dissolve, they do break down over they have a relatively short cycle life. And so with the graphene in there, we get improvements in those parameters. And yeah, we should have something to demonstrate that. Yeah, I should put that in the presentation.
So Michael, you mentioned that the metal oxides, they dissolve into electrolytes, and that using the graphene, it stops. You also mentioned that having the metal oxides coated on the graphene stops the graphene from agglomerating or restacking. So I understand why it would stop it from restacking. Why does the graphene stop the metal oxide from dissolving?
So because it is grown on the graphene platelet, you're only able to dissolve the graphene, the metal oxides from one side. So you've got one side of these clusters, those clusters that I showed. You've got the graphene on the bottom. You've got the cluster on top. You can dissolve the metal oxides and break it down from one direction, and it can change structure. It can crack on that side, but then you've still got that intimate contact with the graphene. So that's the idea, is that one side, yes, that action will happen, but we're also looking at different electrolytes as well to try and avoid that dissolution and breakdown. That's the other angle we're tackling this from, is look at different electrolytes, and also we've got this material that already stops or prevents that dissolution and that breakdown as well. So there's two things that we're working on to try and stop that.
I had another question just based on one of your slides. Are you producing or testing both one side of the separator having activated carbon and the other with the metal oxide graphene? Or are you just using the metal oxide graphene from both sides of the separator?
So at the moment,
and what would be why would you do one and the other?
So what you would do is, this is a bit more technical, so why you would design an experiment the way we have, or the way that we would in future, is that yes, you would have you could have the material on both sides. On one side, you may start to form metal oxides which do not easily change oxidation state, and then you would end up building up products there which couldn't be, there wouldn't be reversible reactions, there wouldn't be these reversible redox reactions, and then you'd end up with a metal oxide product which would just be inert and wouldn't partake in any reaction. And so that is where a lot of time is spent now, is what sort of cell design is the best cell design for this material. And that's something that we have to work out, even though we only, we make the material. It is our problem of how does someone use this material? We need to come to you with a solution of how do we use this material? How do we build it into, how do we tell you to build a device that you can show the benefits of the material? So yeah, that's the next question, is it this asymmetric design with the activated carbon on one side and our material on the other? Or is it we use two different sorts of metal oxide, one metal oxide for one side and one metal oxide for the other, also using the graphene to reinforce that metal oxide and mitigate some of the detriments of metal oxide. So there's two ways we can go. Yeah. Ideally, it wouldn't be asymmetric with the same material on both sides, but there may be a solution that would allow us to do that. But I don't imagine long term that that's the way to do it.
So you're developing the prototype for this with the intention of showing a supercapacitor manufacturer, this is the design that we came up with, and have them go into the mass production of it. So you're licensing the technology at that point.
We would, I think it would be, I don't know how it would work, to be honest. I don't know how that would work. I'll have to, pass you on to someone that would know how the licenses of the
didn't mean to throw your curve there.
Like no, sorry. Yeah, I just make it.
Okay. Okay.
Well, I think that's a good place to conclude this session. Michael, I want to thank you very much. Appreciate you joining us from our good friends over at the Geek in Manchester. And First Graphene is, of course, a member company in the Graphene Council and has been for a long time. Congratulations on the progress you're making in this area. And again, I think this just illustrates the diversity of what's happening in the energy storage, chemistry, and construction sector. So this is exceptionally interesting. Thank you for your participation.
Thanks, Terence.
Cheers.